Hello friends, welcome to this video. In one of our last videos, we learned about the binding energy concept, nuclear binding energy concept. So here we will learn how this nuclear binding energy changes with the number of nucleons. Okay, so the number of nucleons should be plotted along the x-axis, as you can see here, and binding energy per nucleon is plotted along the y-axis, as you can see here. Okay, so this is the plot of binding energy per nucleon, which is measured in mega electron volt, and here it is the number of nucleons in the nucleus along the x-axis. Okay, so you see here, between these numbers 30 and 30 and around 170. Okay, 170 will be somewhere here. Okay, 30 is here. So in this range you can see the binding energy per nucleon is almost constant. Okay, constant means the value lies between 8 and 9 mega electron volt. Okay, so you don't see any drastic change in the value of binding energy per nucleon in this range when the number of nucleons is between 30 and the number of nucleons is between 30 and 170. The average binding energy per nucleon is almost constant. So this average binding energy per nucleon has got a maximum value of around 8.75 mega electron volt at here. Okay, 8.75 mega electron volt for iron 56. Okay, 8.75 mega electron volt, as you can see the unit here. So for iron, the average binding energy per nucleon is the maximum. Okay, and as you come along this curve at for uranium 238, the average binding energy per nucleon is here. It's almost 7.6 mega electron volt. Okay, okay, so now this average binding energy per nucleon, it has got lower values, somewhat lower values. You can see below the number of nucleons. When the number of nucleons is below 30, so its value is quite low, as you can see here. Okay, this value, this plot, this part of the plot, you can see it is quite low, below 30, and it begins to decrease above 170. Okay, so above 170, from here onwards here, so it begins to decrease. Okay, you can see that this curve is decreasing. The plot is um, the value of average binding energy per nucleon plot is decreasing in value. Okay, so we can learn a few things. What does this plot represent? Okay, so what does this plot of average binding energy per nucleon versus the number of nucleons in a nucleus actually represent? So one of the things is that the force is attractive force. Okay, what is the force here? So force we are talking about is the binding force. Okay, the binding force means the force that binds the nucleons in a nucleus. Nucleons means the protons and neutrons. The way they are bound in a nucleus is attractive. Okay, and if you have to break the nucleus into its constituent nucleons, then sufficiently high amount of energy is produced. Okay, sufficiently high energy means energy in the range of mega electron volt is produced, as you can see the unit here already. Okay, so whatever element is there, so the average binding energy per nucleon is always in mega electron volt is produced. Okay, so another thing is, suppose let us consider that just for example, consider that you have to break uranium 238. Okay, you break uranium 238. Okay, so or simply you break this nucleus with nucleon number 238, and two more nuclei you get, which have got the nucleon number says 119 and 119. Okay, So basically you are breaking a heavy nucleus and you are getting two lighter nuclei, each with the number of nucleons equal to 190. So now let us come back to this plot again. So for uranium-238, the nuclear binding energy per nucleon is 7.6 mega electron volt. So now come to the value of 119. So 119 is somewhere here, around here. Okay. So two elements we get that have got nuclei number the no, sorry that have got the number of nucleons as 119, and if you can see, the average binding energy per nucleon is about 8.5. Okay, if you see here, it is about 8.5 or so. That means what? That means here the okay. Let me write again. The nuclear binding energy per nucleon is about 7.6 electron volt, and in case of these two lighter nuclei, the nuclear binding energy is 8.5 mega electron volt. That means what? That means these lighter nuclei, which are produced by breaking this heavier nuclei, they are more strongly bound. Okay, that means you will have to spend more energy, or you will have to spend a higher amount of energy in order to break these lighter nuclei as compared to breaking this heavier nuclei with number of nucleons 238. Okay, so if you have to break this heavier nuclei into two lighter nuclei, okay, because of this change in average binding energy per nucleon, so energy will be released in this process. Okay, so because there is this difference in energy, so difference in binding energy per nucleon, so energy will be produced, and this process is in nuclear physics or nuclear sciences, this process is known as fission. Okay, nuclear fission. Fission basically means breaking a higher nucleus into two smaller nuclei. Okay, so energy would be released, and this is called nuclear fission. About nuclear fission, we'll learn in the next video. And okay, so that is one thing, and another thing is that another thing, point 3. Okay, this was point 2. So you see, very light nuclei. Okay, consider some very light nuclei which have got number of nucleons, suppose less than 10. Okay, less than 10 means somewhere here. So what happens in this case, if you join two such light nuclei, so we will get a heavier nucleus. Okay, so suppose let me give an example. An example would make this better. Suppose two hydrogen atoms, you uh, helium 4 suppose you add two hydrogen atoms. Okay, two hydrogen atoms you add, and you will get one helium atom. Okay, helium nucleus. So, and see, come here. So hydrogen has got some here, sorry, here hydrogen has got this much nuclear binding energy, average binding energy per nucleon is this much, and whereas for helium the average binding energy per nucleon is this much. Okay, so there is obviously a difference. So when two hydrogen nuclei you are combining, so you are getting a heavier nucleus in the form of helium, but from this plot we can see that helium 4 has got higher binding energy per nucleon. It has got average higher binding energy per nucleon. Okay, so in this process also, what will happen? Energy will be released. Okay, energy will be released. Energy release will happen in this process also, just like in this process. And that means helium 4 nucleus is more tightly bound. More tightly bound. Why is it more tightly bound? Because it has got higher binding energy per nucleon. So helium 4 will be more tightly bound as compared to the initial two nuclei. Initial two nuclei means this hydrogen nuclei. Okay, and in this process also energy would be released. Okay, so there would be release of energy. That means if you combine two lighter nuclei to form a heavier nuclei, energy will be released. And in the nuclear sciences, this process is known as uh, nuclear fusion. FUSION, nuclear fusion. Okay. So these are the main points from this particular plot. So attractive forces so between the nucleons. Okay, and when you separate them, some this much energy values in this range, mega electron volt range is required. Okay. So again, if you break a heavier nuclei, which has break a heavier nuclei to form some lighter nuclei, okay, so you will get that the lighter nuclei are more tightly bound with respect to the heavier nucleus. Okay, like take this example of uranium 238. Suppose if we can break uranium 238 to two lighter nuclei, each having number of nucleons 119. Okay, so that will have more average binding energy per nucleon as compared to the parent nucleus. Okay, and in this case energy would be released. Okay, and such a process of binding a heavier nucleus into two lighter nuclei is known as nuclear fission. For lighter nuclei below 10, below number of nucleons 10, so if you combine two lighter nuclei and you can get a heavier nucleus, like these two hydrogen are combined to get helium 4. So in this case, helium 4 has got higher average binding energy per nucleon, and in this case also energy would be released, and the process in nuclear sciences is known as nuclear fusion. And iron has got the higher average binding energy per nucleon value, which is 8.75 mega electron volt. So I hope this lecture has been helpful to you. So please like the video and subscribe to this channel. So thank you very much, friends, for watching, and I will meet you in the next video. So thank you very much.